This problem relies on you understanding what goes in a buffer. A buffer is made up of either a weak acid, emphasize weak, and its conjugate base, or a weak base and its conjugate acid. So if you haven't memorized the 6 or 7 weak acids and weak bases yet, now's the time to do it. Make flashcards or something. Just start carrying them around with you. Okay, so this question is saying which of these will not, and it's a I don't know what you call them, but it can have more than one answer. So let's just go one by one. Can HBr function as a buffer? Nope, because it is a strong acid. Okay, but since the problem is asking which ones will not, that A is one of the correct answers. Ammonia is a weak base, and so far it's meeting the prerequisite. We got to make sure its conjugate acid is present, and it is. So that can make a buffer. Okay, that would make a good buffer, but it doesn't answer the question, so I'm going to cross it out. Hydrofluoric acid is a weak acid, so that's a good sign, right? Buffers have to have a weak acid, and here's its conjugate base, the fluoride ion. Again, since the problem's asking for which will not function as a buffer, that gets crossed out. Sulfuric acid is a strong acid, which means it is not a good buffer. And so that is another correct answer for this problem. And finally, HSO4 minus, in this case, is certainly a weak acid. Okay, its conjugate acid, sulfuric acid is a strong acid, but itself is a weak acid. Here's its conjugate base. So that would also serve as a buffer. So the correct answers, A and D. Okay. We're trying to do this to get you ready for your in-class quiz on Friday. All right, this one, let's see. Now we see that we have a buffer, and it's hydrofluoric acid fluoride buffer, weak acid and its conjugate base. And now it's saying, okay, if you add a small amount of acid to this buffer, what's going to happen to the relative concentrations of HF and F minus? Well, if you add H plus to this buffer, it's going to react with whatever the base in the buffer is. Acids react with bases. What is the base in this buffer? F minus. Okay? So what's going to happen when H plus reacts with F minus? It's going to make hydrofluoric acid. So the bottom line is that the concentration of hydrofluoric acid is going to go up when we add H plus, okay? And the concentration of the fluoride ion will go down because it's been used to chew up the acid. So the correct answer here, looks like I didn't put a correct answer because neither one of them are darkened. But the correct answer is supposed to be this one. This problem is checking to make sure that you understand once again, how to make a good buffer. We've talked about what you need in it, that you need a weak acid in the conjugate base or a weak base in the conjugate acid, but there's also another requirement for making a good buffer, and that is that the pKa of the weak acid you're using should be about equal to the pH that you want your buffer to be controlled at. Okay, so that's really important to understand. So let's look at our options. The problem wants a buffer pH of 5. And so without even doing any calculations, you can look at the Ka values for the two options. And of course, remember what log is. It's simply taking the exponent. So it's very clear already that benzoic acid is going to be the preferred buffer system because it's going to end up with a pKa closer to 5, and in fact it's 4.2. The problem is if you use benzoic acid alone, you haven't met the other requirement in a buffer. Remember, we need to have a weak acid and its conjugate base. If we put benzoic acid in, we're not going to generate any significant amount of the conjugate base. So how do we get that? This is a new concept. It wasn't in my lecture, so pay attention right here. If you manage to figure this out on your own somehow, taking the quiz, that's amazing. So, but don't beat yourself up if you didn't. I didn't really expect you to. But if you have a weak base and that's all you have, and you need to make a buffer, let's say you don't have the conjugate base A- hanging around, what you can do is you can add just a little bit of a strong base, any strong base. So I wrote it little to emphasize it just a little tiny bit. And what will you make when the base that you've added, the strong base you've added, reacts with this weak acid? What you'll get is A-, okay, plus H2O. So there you have actually made the conjugate base in the container itself. And depending on how much OH you added, you can adjust it so that you have half and half of each of these, which makes the optimum buffer. This is a very straightforward, classic Henderson-Hasselbalch calculation. It's a buffer just asking you the pH of the buffer itself before anything has been added to disturb the buffer. So this should have been easy at this point for you. So pH equals, we need pKa, and we're given Ka, so minus log of the Ka, which is 6.7 times 10 to the minus 4, plus log, the concentration of the base goes on top. Sodium fluoride is a salt that is the source of our base. Remember, when you put a soluble salt in water, it immediately dissociates. And so that is how we get the conjugate base to hydrofluoric acid. They dissociate in a 1-to-1 quantity. So concentration of the base is 0.0150. The concentration of the weak acid is 0.120. And if you haven't noticed already, this is not really, it's an okay buffer, but notice that there's a whole lot more of the weak acid present, almost 10 times more than there is the weak base or the conjugate base. That's okay, because if you remember, the range of this ratio should vary from 0.1 to 10, and it does. So I just wanted to point that out. Okay, so if you do all of these calculations, you get, so when you carry out the calculation, you get pH equals pKa, and the ratio of the base to the acid is 0.125. You take the log of that, and pH therefore equals 3.17, which is the pKa minus 0.9. Now I want to point out to you that the pKa is grounded, is primarily influenced by the pKa. This log of the ratio base to acid is going to tweak the original pH, but not by much. That's the whole idea. So it's always going to be pKa plus or minus some smaller value. So in this case, the pH is 2.3 of this buffer, and of course the problem asks for hydronium ion concentration, not pH. You get that 10 raised to the minus pH, and the answer is A. This problem is quite hard, but it's still a problem, a type of problem that everybody needs to learn how to do. But I don't want you to get too frustrated if you don't understand it right away. But do challenge yourself to eventually, before the test, understand it. So here's our buffer system. Notice that this did not tell you it was a buffer system. It's something you need to recognize. So here are some clues for you. Anytime you add a salt, that looks similar in formula to a weak acid or a weak base, you can suspect a buffer. Remember, I've told you before that a salt is a source of the base, and of course, if you ignore sodium, the whole reason we added this was to get the ClO-, which is the conjugate base of HClO. So that is, in fact, a buffer system. It's the first thing you need to do. And that means that you will end up needing the Henderson-Hasselbalch equation. So I would go ahead and write that someplace too. If this were a free response problem, I would probably give you some credit just recognizing that it's a buffer. All right, so now let's look at what we have. You might get excited at first, say, okay, yeah, I can plug these into Henderson-Hasselbalch. It's not quite that simple, though, because we have added an additional component. So basically what's happened is we added a strong base in order to disturb the buffer. So that strong base is going to react with the buffer, and that means that you need to set up the chemical reaction that occurs. Okay, so write balanced chemical reaction if it's a buffer that's been disturbed. And so you have to decide what it's going to react with. NaOH is a base. Which one of these components of the buffer will it react with? Bases react with acids. So now you have got to write the reaction between the weak acid that's in your buffer and the strong base that you just added. Whenever I see a sodium ion, I like to work in net ionic equations. You don't really have to. I think it makes it more simple. So whenever I see a sodium ion, I know that they are always spectator ions, and I'm going to ignore them. All right, so here's the reaction. Since it's a strong base, it is going to go to completion. There's no equilibrium when you have a strong acid or base. And what's going to be formed is water plus some more of that conjugate base. So what's going to happen to this ratio of base to acid when we add this strong base? The amount of the weak acid is going to go down because it's been chewed up by the hydroxide, and we've made more of the conjugate base, so that's going to go up. So this numerator is going to go up and the denominator will go down after we add hydroxide. So we have to figure out how much of each of these we have before we plug into the Henderson-Hasselbalch, which means we need a mole table. This is quite a complex problem and probably will be a free response problem on your test. I'm going to go ahead and open up another page to work this out. So in order to complete the mole table, it's a little bit like an ice table, but it's trying to determine the moles of things in a chemical reaction. When you are working with stoichiometry and chemical reaction, you need to be in moles, not molarity. And so we need to figure out how many moles we have of everything. And then I'll show you how to plug them into the mole table. So we have 100 milliliters of both components of the buffer. And rather than convert that milliliters to liters, I'm going to keep it in milliliters, and that will then give me millimoles instead of moles, which is just fine. So I have 100 times 0.125 is 12.5 millimoles of HClO. And when I multiply 100 milliliters, it's a solution of both of these, times 0.130, I have 13.0 millimoles of hypochlorite ion. Okay, so now how many moles of NaOH have I added? The problem says we have added 2 milliliters of 0.1 molar sodium hydroxide. So again, just multiplying those, I get that there are 0.200 millimoles of sodium hydroxide. So now I know all of the starting moles that go into my mole table. So we'll go to the mole table now and plug these values in. All right, so we have 12.5 millimoles. I'm going to stop writing units in all of them. And 0.2 of hydroxide Water doesn't participate. And we have 13 millimoles of ClO minus. Okay, that's our before. Oh, I just kind of, you don't have to call these. I was playing and saying, okay, that kind of spells bad or bad, you know what. So anyway, I was amusing myself. But anyway, during the reaction, all of the hydroxide added is going to react because it is a strong base. So after the reaction, there's going to be 0 millimoles of hydroxide left. That'll always be 0 when you add a strong acid or strong base to disturb a buffer. And since it's all a 1-to-1-to-1 stoichiometric ratio, we're going to subtract 0.2 from the weak acid. So its final amount is going to be 12.3 millimoles. And we're going to add 0.2 millimoles to the ClO minus because we're forming more of that, and so we're going to have 13.2 millimoles of that. So now you have the final or equilibrium amounts of the original weak acid and its conjugate base. So now you can plug these values into the Henderson-Hasselbalch equation and figure out pH. Here's the pH equation, Henderson-Hasselbalch, and pKa, they usually give you Ka in the problem, is log of 2.9 times 10 to the minus 8, and that equals 7.54. So plugging that back into the Henderson-Hasselbalch, we know that all the pHs we'll get for this buffer will be pretty close to that pKa. And now let's plug in the values we have for the conjugate base and acid. That's 13.2 millimoles over 12.3 millimoles. The really nice thing about Henderson-Hasselbalch is the fact that this is a ratio of two components, so units cancel, and that's why you can either have units of molarity on top and bottom, or units of mole on top and bottom, or units of millimole on top and bottom, because the units end up canceling. You just can't have grams, but moles or molarity is fine. And now plugging all that in, we get, so our final pH after the addition of that dab of sodium hydroxide is 7.57. That's not very different from the pKa, and that's what we expect for buffers. They do a really good job of managing a stable pH. That's it for working out the problems for your sample quiz. Remember that you have an in-class quiz Friday, and it's going to take a lot of practice to do well in that. So make sure that you work on either mastering and or the sample worksheet that I've posted in D2L for buffers.